Who here has participated in a debate competition before? None. Okay, wow. Okay, not a very outgoing crowd, I see. But do you follow presidential debates in the US election? I don't know if there's an equivalent in the German political landscape, but yeah, I mean, you should be aware that it's a very hotly important aspect. I'm not? Oh, okay, sorry. Oh, you mean on the Zoom? Ah, okay. My bad. My bad. Okay, there we go. Yeah, it's all good. All right, so the idea is basically that if you have watched these debates in a political context or in a discourse, even in a legal setting, a lot of the consequence is influenced by the arguments that are made in the debate, right? You can see like after a presidential debate in the US, you'll see the polling opinions of people, like maybe they are leaning more towards the Democratic candidate as compared to the Republican candidate because the candidate made some specific arguments that aligns well with their beliefs or the incentives. But there's not a clear perception on why you might favor a specific candidate's argument as compared to another candidate's argument. You can be biased, like maybe you don't like me, so regardless of what argument I make, you'll probably say I'm the worst debater on the planet. But in the same regards, you might be biased towards liking me and you wouldn't just hear the content of my argument, but just because you like me, you'll say that my arguments are stronger, right? This question has plagued humanity since like God knows when, because since the time society formed, everything that governed the societal aspects were discussed by debates, right? During the time of the Greeks and Romans, you had the men voting in consensus in a sort of a agora platform for any specific law that was supposed to govern that society. And since back then, this voting has shifted from the fact that it can be majority rule or it can be other aspects. And this also is a very valid problem in social choice theory. For instance, in elections, how people vote and what voting theorem is used. So if you know Moritz Hart over here, he works a lot on this aspect. And there's a lot of science that has been built on this problem. Like if you know Condesert's theorem, it sort of is a defining aspect of this problem. So today we'll be only looking at a small, narrow scope of that problem, where we are only interested in saying, can we find a better, auditable, transparent way of ranking arguments in a discourse, right? And this discourse can be anything. It can be a debate, dialogue. It can be a heated Twitter discussion with your ex if you are into that. But it's just any platform where we can have exchange of statements, right? We're not interested in factual accuracies of the statements over here. So just a TLDR. We're only interested in seeing how we can have a ranking operator on this on the list of arguments that are made in the discourse. This work is in collaboration with my advisors, Antonia and Vulcan, and also with Radiate, all of them from here and from EPFL. You can scan this QR code if you want to learn more. There's actually an interactive playground where you can actually write your own arguments and see how your arguments does. Cool. As I said, like societies have been built on the platform of debates and discourse. We have arguments that people make, and then we decide how we can make laws off of these arguments or settle disputes, legal platforms, and we decide what counts as the oracle or validator of a particular statement. But in the past, of course, this was done through a vetted person or an institution or a jury. But now we have these fancy toys called large language models that do a lot of this in a lot of context. For example, there's a platform called Decide Madrid. Is anybody from Madrid here? No? Okay, so in Decide Madrid, it's a citywide platform where the city authorities propose certain laws, and the people of Madrid can go and provide their opinions. And then the city collects it and sees whether if we pass this, whether this public would like it or not, for instance. But of course, getting opinions from people is costly, expensive, noisy. So we try to use proxies like language models. But these language models have a much bigger problem that we know about is that if you use LLM as judges, they have a very high disagreement rate, which means that if you ask the same argument to different language models, then they will give widely different opinions, scores, ranking, whatever you might say. This problem is nothing new to the work that we did. It's very well documented in a lot of literature. They call it substantial intermodal disagreement. But in the context of debate, it is even very dominantly observed. So like just asking the same argument and asking it to rank it amongst all the arguments possible. If you just ask different language models, they will give very wildly different ranks, which is shown by the red dots here. But the method that we propose like sort of consolidates that to make it much more closer to a consensus. And actually, the funny thing, when we did this project, we actually observed that certain models have very high agreement rate with certain class of models. For instance, a lot of the Chinese models like Qwen and DeepSeek have a very high agreement rate with Gemini for some reason, and very high disagreement rate with Claude. This maybe gives some intuition that maybe DeepSeek is distilled from Gemini. I don't know. I'm not going to make any accusative comments over here, but that was an observation that we found which was very interesting. Okay, so the key part of why this problem is so dominant in language models is because we ask for a global ranking. We give it an entire debates transcript, like whatever 100, 200 arguments, and we say, okay, rank them. We of course give it some grounding, like rank them based on certain properties like factual correctness or whether the argument has valid substance in terms of the debate's theme. But it's a very hard problem to do in a global context. Even if you ask humans, they will also have very widely different rankings that they will reach to. But instead, if you look at local properties in this argument graph, so we can construct a graph of all the arguments made in a debate, then the local properties become much more stable, which is to ask, if I give you this argument and this argument, can you say if this argument contradicts this argument? That is much more easier to say than asking a model to rank 100 arguments in a global sense, right? So the key observation is that aggregating these stable local judgments into a global ranking with a deterministic operator is way more plausible and auditable than just asking a language model naively to rank all the arguments in a debate. This has been studied since also millennia. There's a framework in symbolic AI called abstract argumentation frameworks. This was proposed by a Vietnamese mathematician. I don't know his first name, his last name is Dung, in 95, and where each argument was represented as a node, and you can construct this interaction graph of arguments, and then you just see the directed edges, and here edges correspond to whether an argument is attacking another argument. Here, arguments are not natural language arguments. This has been since the 90s the primary way to verify lemmas of a proof. So you see if a lemma contradicts with another, and then you can find a set of acceptable lemmas, right? So the criteria over here is acceptability, which is that an argument, in this case a node, is acceptable as long as it is defended from the attackers that it receives. That's the idea. So it's a binary 1 or 0 label, right? And this has been studied under this field called as argument semantic theory, and where you given an entire list of arguments or lemmas or whatever it can be that you can represent in this form of directed graph, you basically get two sets out of it, a set which is acceptable arguments, a set which is unacceptable arguments. Right? So there is no ranking. If you get a set of acceptable arguments, let's say out of 10, 5 are acceptable, there's no ranking of which out of the 5 are ranked higher than the others. Because in case of a lemma, right, where you want to see the acceptable list of lemmas, there's no point of ranking. As long as you can find the set of acceptable lemmas, you do not gain any extra information by ranking the lemmas itself because they are all acceptable. So we extend this to a graded strength semantic, so no longer relying on binary cases. And we design a very simple operator. So this is what the operator looks like. The numerator is basically rewarding an argument. So G of Sj is basically the strength of an argument, J, and we reward it by the total incoming defense it receives, right? So how many arguments in that graph are defending this argument or supporting it? And the denominator is penalizing the argument by how many or how much total attack it receives, right? So how many arguments are attacking this specific argument and by what strength, right? So we run this operator in a sort of an iterative manner with, of course, some damping, as the last line says. And it converges to a set of strength values for all the arguments in the interaction graph. And then you can just sort them based on strength and you'll get your ranking. So you might ask, like, what is the attack over here, like Wij, which is the attack matrix? It's an n squared attack matrix. And what is the dkj, the defense matrix? So the attack matrix here we construct very simply. In classical literature, this was denominated by symbolic rules, but because we are operating in natural language arguments, we cannot extrapolate those rules. So we simply ask the language model to say whether argument A is attacking argument B, and within a fixed strength score, like between 0 and 10, for instance. And the defense is very interesting over here because we use an interesting human property in defense, which is that the enemy of my enemy is my friend principle. So defense is essentially W squared, right? Because if you can formulate W and you just take the square of it, that tells you the weight of the support that you're receiving from another argument because it is attacking one of your attackers. That's what it is. But you can come up with a lot of different defense formulation, and we tried that. But for this paper, we use W squared. I'll skip this. This is a toy setting which explains how the ranking works. But the interesting fact is that this operator is fully guaranteed convergence. So you can actually mathematically prove under some assumptions that it converges with the Banach fixed point theorem, and it has a unique fixed point, which means that if you run it n number of times, you reach the same conclusion, which is what we want. Because if you just simply ask the language model n different times to rank the same arguments, it will give you validly different rankings if you are using a non-deterministic temperature, for instance. But using this, you always converge. And it's finite step convergence, so it converges in less than 50 steps usually in our analysis. But these are worst case bounds, so you can see the paper for more details on this theory. Now you might ask, like, why are we ranking in this property, which is that why do we rank based on how much support you get and how much attack you receive? This actually exists in argumentation theory called as global sufficiency. Global sufficiency is a metric in argumentation theory where you say an argument is globally sufficient if and only if all possible attackers to that argument, irregardless of whether it is in that graph or not, or it can be even hypothesized, are negated for. Which means, let's say I make an argument that pizza is better than Maultaschen. Okay, yeah, I know. Maybe this is a strongly consensus argument, but regardless, you might come up with a lot of possible counter argument to this, which might not be within the graph itself because it can be hypothesized. But globally sufficient says that my argument that I just made can only be globally sufficient if all the possible counter arguments are negated for. But this is a very wildly creative metric because you can assume a lot of hypothetical arguments, and it's impossible. That search space becomes very big. So we ground that search space only to explicit attacks and supports within the interaction graph itself. So we do not take into account any hypothetical arguments that one can make. Because imagine in a debate, you only get rewarded by the judge if you made that argument, not because there is a possible argument that could have been made, but you didn't make it. That makes no sense, right? So that is what we construct, and we call it structural sufficiency. And we actually prove that our metric grasp is a graded propagation-based analog of this theory of structural sufficiency. So it suffices and supports all the axioms. There are 4 different axioms of structural sufficiency. It suffices all of that. So we construct some data sets and we use some judges to do our primary analysis. And our primary analysis is that if you use our method as compared to raw, which is just directly asking a language model to rank all the arguments, raw plus SS is where we ask the language model, but we optimize the prompt. We always have much higher consistency rates across all the different language models that we try, across all the debates, which means that models now tend to agree on which arguments are ranked at which position as compared to, yeah, just like directly asking the model to do it. Okay, so the last thing I want to confirm is that you might say, okay, why should I use this? Like, because in a debate, a lot of the time, the conclusions that are reached to is based on convincingness. I might make a very poor argument, but I might convince you that it is a very good argument, and you might weigh it much higher than a better argument that was made. So a lot of debates do rely on convincingness, and we actually measure against a data set by IBM called Debate Decision Outcomes against human labeled convincingness scores, and we are not aligned with convincingness. So we do not measure convincingness. This is important because convincingness is a very subjective holistic metric, and it would be very hard for us to mathematically represent that in a graded operator form. However, in the paper, we show that we have a very high correlation with human graded attack scores, which means if a human said that an argument is contradicting another argument, that we do correlate with. So yeah, just the takeaways is that what we propose is a deterministic convergent operator that takes stable local attack and defense judgments into a reproducible global ranking. We have much higher agreement, in some cases more than 2x. We are robust, convergent, and we provide an honest auditable scope, which means that you now know why a certain argument is ranked higher than another argument. There are some limitations, of course, which is the O of n squared pairwise scoring that we have to do, which we can mitigate by doing it block sparse. We haven't tried it. But you might ask now, why should I even care about this in a deep learning context? Like you work on different stuff, probably not debates. Is that this idea can be now taken to LLM as judges for post-training, where you now get scores on traces, right? But if you ask different models, you'll get very wildly different scores. And you're now optimizing a reward model against those scores. And your reward model will sort of represent the bias that the judge that you're having. But instead of doing naive LLM as a judge, you can now make it stable by using this operator, where you'll get a much more consistent reward model that you can use for post-training, which is what we are currently working on. That's all. But I would like to take a 10-second opportunity to show that you could go over here, and there is a try it page where you can try your own arguments and you can get an ELO ranking of how well you do, essentially, right? So you can select motions over here, and we also have custom motions to actually we pull hot news articles and we create debates topics from that. You can take that, for example, you can write your argument, you can make some structural assumptions, and then you can run the full thing and you'll see interactively what it does. Okay, that's all. If you have any questions, I'm happy to answer.